So thank you so much for having me. The Collective Intelligence Conference is one of my favorite conferences, so it is really an honor to be invited and to get the opportunity to talk about some of the work that we've been doing and really excited about. So the thing that I'm going to talk about today is an ongoing project, and it's been ongoing for a couple of years now, and probably it will continue to be ongoing for a couple more. I already see that some of the people who are in attendance today have heard me talk about this in the past, or we had extended sessions discussing this. For those of you who've already heard some parts of it, consider this kind of some sort of a progress report and seeing some of the new results that emerged from this project. And for the rest, I'm going to go over the motivation and the setup, and also kind of the plan of how we are going to move forward in this. So with that being said, there are really two things going on in this talk. The first thing is the substantive problem that we're interested in, which is the problem of developing a language or some sort of a representation to describe tasks that can be performed by collectives when we are studying questions related to collective intelligence. And this is kind of the thing that I really been focused on for the past couple of years. But also another thing that's going on here is more of a methodological perspective that we call integrative experimentation, which will become much clearer as we go through some of the slides in this talk. But basically, what I'm going to do today is to talk how are we going to use this integrative experimentation approach in order to better understand the role of tasks in determining collective intelligence. So to motivate this, I don't need to spend a lot of time to convince you that team performance is something that academics seems to be interested in. Researchers from many different fields are producing many different papers on the topics for almost half a century at least now. And luckily, it is a problem also that is of practical interest. You have managers and HR departments all worried about how to optimize team performance on particular tasks. And roughly speaking, a good big chunk of this literature is about the question of synergy. Or in other words, should we bother with teams at all, or are we better off assigning our tasks to individuals who can work on them independently, and then there is some sort of an external observer like a manager who can aggregate? So it is the question of, if I have something to be done, should I hire 3 people, have them work together and produce one output, or should I hire the same 3 individuals, have them not interact with each other, and then I get to kind of aggregate or pick which answer to go with? And another big chunk of this literature is more about team composition, which is concerned with what makes some teams perform better than others. Why, when you put a bunch of individuals together and they get to interact, sometimes they become synergistic and they can do really well and exceed the performance of even the best individual within the group. And sometimes you put individuals together and these groups end up being plagued with process losses and not doing as well as even the average or the worst individual in the group. And surely researchers were able to generate a very long list of things that seem to matter in determining collective intelligence. And the problem is that the literature is also filled with inconsistent and seemingly contradictory results. So if you pick any of these attributes, and actually I started with kind of getting involved into this literature by looking at communication networks and how network structures can affect these collective outcomes. But then for any of these attributes, if you look at the work that has been done, you will find all kinds of results. So for example, if we look at something like cognitive style diversity, then you will find evidence and theories for why cognitive style diversity would improve collective intelligence. But at the same time, you will find evidence and empirical work that will show that cognitive style diversity hinders collective intelligence, and also some results about it having no effect on collective intelligence. So for any of these attributes, of course, it is a little bit more subtle and nuanced than this, but for each of these attributes, you could easily find evidence that goes in either direction, a positive, negative, or even in some cases, no effect on team performance and collective intelligence. So if you are a manager who's trying to use kind of science in your practice, you'll have a hard time figuring out what to do. And because anything that you do, there is something in the literature that will tell you that this is the best thing that you could have done, the worst thing that you could have done, and probably it had no effect on the outcome of interest. And what I want to be clear about is that I don't think the problem is that we lack theoretically informed hypotheses about the causes and predictors of collective performance. It's quite the opposite. We have too many hypotheses and empirical and modeling results. And what is unclear, it's under what conditions any of these results and theories hold and apply. So after obsessing over this problem for a couple of years now, it's clear to me that the answer to these questions highly depends on the details of the task being performed. Now, I'm going to start with this overly simplified and naive hypothesis for an illustrative purposes. That's why the asterisk. I'm going to make it a little bit more kind of comprehensive and potentially realistic, but for now, just let's assume that this is my hypothesis. I claim that if we have better understanding of the tasks, the thing that the crowd or the collectives or the teams are trying to do, we will be able to reconcile these puzzling patterns in the literature. So the relative importance of something like the communication network or skill diversity or cognitive style diversity changes magnitude and sign as a function of the task that is being performed by this crowd. And the main or the most important concept for testing this hypothesis in our project is what we call the task space, which is an abstract space where all tasks live. So you can think of a population of tasks, so any possible task as a row in this matrix, and each column is a feature or an attribute that captures a dimension about that task. And this is kind of an abstract concept in order to operationalize some version of it for us to be able kind of to test this hypothesis that things vary as a function of the task. We actually have to have something that is a little bit more concrete and less abstract. And to do so, one thing we did is kind of populated this matrix by going back into the literature and looking at every experimental paper that has been done in this literature that we were able to find and extract the tasks that has been used in those experiments. We ended up finding around 250 unique tasks. So many of the tasks are being reused in many of these studies, at least the task class. And I'm going to be a little bit more precise about what do we mean by a task in a little bit. But eventually we ended up with, and this in itself took us a little bit more than a year to come up with an initial list of tasks, eventually with a little bit of cleaning and also filtering. So one thing that we required for our project is that the tasks can be done in principle by individuals and by groups, as we are going to compare performance of interacting groups versus individuals working independently. That really eliminated many of the tasks because it as it turned out, many of the tasks that people studied in this literature, things like cooperation tasks or sometimes coordination tasks, are undefined or not applicable at the individual level. For example, you couldn't have a single participant or a single player who would play something like Prisoner's Dilemma or a negotiation game or a graph coloring game. You will need, it's undefined at the individual level. So once we do this filtering, we end up with 71 tasks for now. And I'm going to expand on that a little bit. Then for the features, so to populate the kind of, to define the columns of this matrix, we looked at the union of all existing taxonomies about tasks. So there are a bunch of taxonomies. They are listed in here. I'm not going into the details of what these are. And if you're not familiar with them, I don't think it's gonna matter so much. The most important thing to get out of this is that we, rather than focusing on one taxonomy, which has typically a lot of taxonomies kind of vary in terms of their pros, cons, and also like their applicability. We are looking at the union of everything that we were able to find in the literature that relates to the task when they are performed by groups of individuals. And we end up with 23 dimensions that are extracted from those taxonomies. And then we actually had trained coders who would actually go and look at each task that we've extracted, and they would rate them along these dimensions, and we end up with something that looks like this. So we have a matrix, this table of 71 tasks by 23 features. So for each task, something like checkers, we would have a vector, a 23-dimensional vector that describes that task. And as I am kind of a very visual person, and sometimes it's kind of reasoning about matrices and high dimensional vectors becomes a little bit tricky, I think it is helpful to try to visualize what this looks like. A word of caution: this is a two-dimensional projection of the matrix, and this is the real data that we have. However, everything that we are going to do, we are doing in the full 23-dimensional space. So these visualizations are kind of just to talk about the intuition of what's happening and what we are doing with this and how can we test the hypothesis that I posed. However, don't be bothered by what these two dimensions actually mean or how much they explain of the variance. We're not actually operating in the two-dimensional space. Everything we're doing in the full 23-dimensional space. So one thing that you can kind of get, and again, imagine that it's happening in 23 dimensions, you can see that tasks are distributed across this space. So for example, and there is some notion of distance or similarity. So you can see that something like the word construction from a subset of letters task is closer to the word completion given a starting word task. However, they are very different from writing an ad, but writing an ad and summarizing a discussion and writing a story are kind of closer to each other in this task space, and they are quite different from checkers or 9-dot problem or the desert survival task. So you have come to some sort of a distribution where each task that has been used in the literature is a point in some high dimensional space. Then we can ask a question like, do groups outperform comparable individuals? So this is the synergy question. And there are, let's assume that there are 3 possible answers to this question. There is no synergy, which means that the interacting individuals are no better in doing the task than the average individual within the group. So the group is no better than the average individual. That's another way of saying it. Weak synergy is if the group outcome is better than the average individual in the group, but not better than the best individual in the group. And then strong synergy is if the group outcome or the group performance is superior to that of even the best individual in the group, right? So actually, it is a more of a continuous measure, which is how much synergy there is. But now let's just categorize, treat it as these 3 categories. So typically, when we want to answer this question, we pick a task and we do this, right? So we pick something like the room assignment task. I've done that in the past. So this is kind of, I'm speaking of experience. Sometimes we pick this task in some ad hoc way, just because we think it's a good instrument to measure the thing that we care about, or because some other people have used it in the past, and then we need less justification of why we are using this task. So we pick a task like the room assignment. We implement it. Basically, this task, you have a bunch of students, you have a bunch of dorm rooms, you have to assign the students to dorm rooms. The students have preferences of where they want to live, but also they have constraints. So some students, they don't want to live together. Some students can, they don't want to be neighbors and things like that. And you have to kind of figure out a solution to this problem. So we have people come in online, they are working on this problem simultaneously. They can chat with each other and they can reach consensus on solutions. And then we randomize people into either doing this as part of groups, interacting groups, or individuals. And then we end up with finding that the answer to this question is that there is no synergy. So actually, teams did no better than the average individual within the group. And then we have all kinds of theories that allows us kind of to generalize this a little bit more to say that, you know what, there is a balance between process loss. So there are things like communication cost as well as probably social loafing and groupthink that really hindered groups from really realizing their potential. And there are, of course, things like parallel processing and other benefits of being in a team, but the cost of being in a team overweigh the benefit of being in a team. And using that theory, now we know that the answer to this question on this task is red, no synergy. We write the paper with our theory as if the entire space is red, right? So there is no group synergy because teams are plagued with process losses, because no one really in the real world or other people, other researchers care about the room task, the room assignment task in particular, but we care about what we learn from it in order to generalize to other instances. However, the knowledge that we generated by running that particular experiment looks more like this, where probably the answer is red, so no synergy for the room assignment task, maybe for other constraint satisfaction and optimization tasks, maybe to other problem-solving tasks, but we know very little about whether that results actually hold for a task that is quite far in the space of tasks like the 9-dot problem. So what we do in this kind of integrative experimentation approach is that we are not done by running this experiment on one task, but then we pick another task like the 9-dot problem. We implement it, we bring people into our platform, they perform this task, and then we find actually weak synergy. So the answer to that point in the space is green. So now we update our theory about the balance between process loss and synergistic gains and say that for this range of tasks, we find no synergy, process loss overweigh synergistic gains. However, for this region in the task space, for this range of tasks, the answer is green. It's like weak synergy. And we have kind of these boundary conditions that split them and a prediction about every point in the space, what the color is going to be, what's the answer that we're going to find. However, by running these two experiments, this is the knowledge that we generated about the space. We have very little prior about whether our predictions or our results hold for that point in the space. So we go and pick that one and do that iteratively. So what I want to kind of emphasize is these two steps that we have them in our case as models. The first step is learning the importance of the different factors. So having some sort of a model that looks at the results from all of the experiments that we already ran and then makes prediction about all of the experiments that are yet to be sampled. So this is kind of the coloring of the space. We have a model that looks at the points that are sampled and then tries to color the space by making predictions about every point in the space. So this, what we call is the theory generation model. It's kind of, it explains existing data, but also it has implications or predictions for experiments that are yet to be sampled. And then we have another model that we call it the adversarial theory testing model, which is a model that is rewarded for picking an experiment that falsifies the theory generation model. So we have these two competing forces. A model that gets rewarded for making accurate out of sample, out of distribution predictions, so predictions under intervention. And then we have another model that gets rewarded for falsifying that model. So for picking examples or experiments where the first model is most likely to be wrong. And by doing this iteratively, you end up with a segmentation of the design space of tasks to say that for this region in the space, the strong synergy results hold. However, for this region in the space, there is no synergy. And in this corner, there is weak synergy. And if we have a theory like this synergistic gains through things like parallel processing and exploration of solution spaces and process losses like social loafing and cost of communication, you can see how the balance of those things change as a function of where you are in the task space. So although these points are real data and we've been running these experiments, the actual design space of our experiments is a little bit more complicated, and the colors that I was drawing before are more illustrative and toy kind of example to illustrate the intuition. Now I'm going to show you some real data from the pilots that we've run. So we have 71 task classes. So the room assignment is one task. However, each task, we can vary the complexity of its instances. So for something like the room assignment problem, we can change the number of students that you have to assign to the dorm rooms, the number of dorm rooms, and the structure of the constraints, and vary the complexity of the task significantly. So for every task in the task space, we can vary its complexity. So we have 3 levels of complexity: an easy version, a moderate version, and a very hard problem or version of that task. And we have 4 team sizes. And that gives us a total of approximately 850 possible experiments to sample from the design space of experiments to answer the question, do teams outperform comparable individuals? So in our pilot, so we are still haven't put the trigger on the actual experiments. The pilot, we sampled 86 experimental conditions, and we have 8 trials from each condition. So this is the actual the expanded design space that includes complexity and team size as dimensions. So the size of the marker is actually the team size. And for each point in the space, we compare, it's actually the difference between 2 points, having individuals do the tasks independently versus a team. These are the points that we sampled or the experiments that we sampled in our pilot. And this is what we actually, the realized outcome. Again, everything is happening in, this is like now 25 dimensional space. So although there is some clear separation and we have models that were able to make reasonable predictions on holdout experiments, it seems a little bit more overlapping in this 2-dimensional projection. But also there are, so this is kind of where we're heading. This is only the pilot, the actual experiment. We plan to sample 300 experiments out of the 800 possible experiments that one could run. But this is still an ongoing thing as we implement those tasks and some of the logistics of operationalizing this. So there are a few more things that I want to kind of, I know that I'm a little bit over time, but let me go through this relatively quickly. There are a few more things that we can do once we defined this task space. It can guide future research by generating new tasks. So one thing, all of the tasks in our space come from the literature. There are regions in the design space, so tasks with certain characteristics that don't appear in the literature. So these are empty regions in the space. And because tasks in the literature aren't sampled in any systematic way, we can generate new tasks to fill in the gaps or tell you what are the tasks that are understudied in the literature. We can generate new features. So we are already seeing this in our pilot data. You have 2 different tasks that have identical values across all dimensions. So from the perspective of the task space, they are identical tasks. However, they have systematically different answers when we ask the synergy question. So they have different colors. And this indicates potentially a missing dimension from the existing taxonomies about tasks that could differentiate or pull away these tasks from each other in the task space. So that's kind of generating new theories by adding more columns to the task space. It can examine the limits of generalizability. So if we ask this question and we found that there is weak synergy everywhere in the space, so the whole space is colored green, then we've discovered a universal law. This is unlikely for any of the social scientific questions or collective intelligence questions that we are asking. Another potential, so kind of going in the middle of that spectrum of generalizability, you have theories of the middle range, which is kind of what we're finding an evidence for, which is it depends. So there are regions in the space where different results and theories hold. And there is no universal theory, but we have kind of these theories of the middle range, and knowing where you are in the design space will tell you which theory actually applies to your context or situation or task. And then there is kind of at the other end of this spectrum, you have no hope or existing theories, which is any perturbation in the design of the experiment, changing any of the parameters of the tasks, gives you completely a different answer in no particular pattern. And there is no predictability from previous experiments that will allow us to generalize to new experiments, which will be an interesting finding in itself and poses some interesting questions about what does social science can do for those kinds of domains or those problems. And we have actually a prospective piece that if we were living in that world, how would we do social science? And of course, one simplification I did in this entire talk is that I talked as everything is determined by the task space. However, for collective intelligence to be measured, you have to have a group of actors which will define a team space. In this case, we varied a couple of parameters about the individuals. However, it's just a very small region in the possible actors that we are including in our experiments. They have to do something, which is the task, but we fixed the process space. So they have to do the task under certain conditions, something like our experiments are online. They interact through a chat rather than face-to-face interaction. They have to reach consensus, so we don't have leadership or hierarchy. So there is a process under which they have to perform the task. And then we scanned the task space. So we looked at a small area in the team space, a single point in the process space, and then scanned the task space. However, one thing that we can do from doing this is that by doing what we've done, we can, for example, if someone is interested in how these results vary, if you go from online experiment to face-to-face interactions, because maybe something like social perceptiveness only works when people can look at each other and read each other's body language, and that's a reasonable hypothesis. One thing we can do is use our model to predict what is the most informative face-to-face experiment. Because face-to-face experiments are quite expensive, we can be much more efficient in picking those face-to-face experiments by running those online experiments. So we built a bunch of tools that allow you to do this. So we're doing this with Empirica. It's high throughput, like this sampling of design spaces of experiments can be automated, and it integrates with crowdsourcing platforms and tools for optimizing hyperparameters of experiments, and those are all publicly available and open source tools. And thank you so much for your time, and apologies for kind of going over.
That's okay. Thank you so much, Abdullah.